To simplify this, we want to come up with a relatively easy way of predicting whether or not a molecule is going to have a dipole moment or not, recognizing there are potentially exceptions to this very simple rule. So, first of all, one of the rules that we can sort of count on is that if the central atom contains a lone pair, then probably this molecule will be polar. One of the criteria will be whether or not the bonding electron regions are polar covalent bonds or not. But usually if you have a lone pair that's on that central atom, it's probably going to be a polar molecule. So, as an example of this, here is ammonia, which adopts a trigonal pyramidal type structure. The NH bonds are polar covalent bonds. There's pretty significant difference in electronegativity between nitrogen and hydrogen. The electron pairs that are shared are pulled more closely towards the nitrogen, and so the three of those, if are broken up into components, then produces a dipole that is pointed towards the lone pair. And in fact, the measured dipole moment for ammonia is 1.42 dBs, which is slightly less than that for water, but still a very significant dipole moment. As a further example, we have NF3. In this case, the fluorines are quite a bit more electronegative than the nitrogen. So now the bond dipole moments are pointing towards the fluorines. And of course, this also adopts a trigonal pyramidal structure and results in an overall vector that is pointed away from the lone pair in this case. But its overall dipole moment is now quite a bit less as a result of that. And then finally we have something like fluoromethane. This is a tetrahedral molecule. The carbon-hydrogen bonds are essentially non-polar covalent bonds, so we don't have a vector for the CH bonds. But fluorine is quite a bit more electronegative than carbon, so the electrons in that bond are drawn towards the fluorine. This results in a net dipole moment of a considerable 1.85 dBs. So, as some examples of this, we want to look at each of these molecules and predict the molecular geometry and determine whether or not the molecules are polar or possibly nonpolar molecules. So, as the first example, we have HCl. HCl, we would consider the chlorine to be the central atom. There are only two atoms in the structure, so there's only one possible molecular geometry, that is linear. We can ask ourselves whether or not there is a polar covalent bond present in this molecule, and in fact, chlorine is quite a bit more electronegative than hydrogen, so there is a bond dipole. And there are lone pairs on the chlorine, and this suggests that there should be a asymmetric structure, and the molecule should be one that has a dipole moment or is polar. And indeed it is. In the case of ammonia, NH3, this adopts a trigonal pyramidal structure. There are 4 electron regions around the central atom, 3 of them bonding, 1 of them being a lone pair. And so this adopts an electron region geometry of a tetrahedron. When 3 of them are bonding, this forms the trigonal pyramidal structure. The bonds are indeed polar in this case, and of course the bond angle is approximately 109.5 degrees. The bonds are polar, and there is a lone pair on the central atom, the nitrogen, so we would predict this to be a polar molecule, and indeed it is. And then finally we have BF3. In this particular case, we have three electron regions around the boron, so this is a trigonal planar structure. All three of them are bonding, so the molecular geometry is described as trigonal planar. The angle will be approximately 120 degrees. We do have polar covalent bonds, the fluorine being much more electronegative than the boron, so we have vectors that for each of these BF bonds. But in this case, it's a very symmetric structure, and there are no lone pairs on that boron. So this ends up having no net dipole moment, and therefore it is nonpolar. So one last thought about dipole moments in terms of molecular shape, and some exceptions to this little rule that we just discussed about the lone pairs on the central atom. In the examples that we have here, we have chloromethane compared to tetrachloromethane. In this particular case, both of them have 4 bonding regions around the carbon atom, so we predict a tetrahedral structure in both cases. There is a slight distortion for the chloromethane because of the differences in the size of the chlorine versus the hydrogen atoms. And so we predict that the angles will be approximately 109 degrees, but a little bit of possible distortion because of the differences in sizes. So the difference in electronegativity between the chlorine and the carbon would result in there being a polar covalent bond here. But the problem then becomes, is there a net dipole in this particular molecule? And in fact, since the carbon-hydrogen bonds are essentially non-polar covalent bonds, we would then predict this to be polar. So even though this molecule does not have a lone pair on the central atom, it is a polar molecule. In the case of tetrachloromethane, in this case, then the molecular shape is also tetrahedral, angles of 109.5. There are 4 different polar covalent bonds, all pointing to the corners of a very symmetrical structure. No lone pairs on the carbon in this case, and this is not an exception to our little rule about the lone pairs. So this is indeed a nonpolar molecule.